Okay, good morning. Happy election day. We'll be going over some vocabulary. A lot of this will be things that we did yesterday, but it's good review. And this is about atomic structure, which is one of the most important parts of chemistry. If you understand atoms, you can understand how atoms will join with other atoms and create compounds. And that's really what chemistry is all about. So we start with the very basic definition of what an atom is. And an atom is the smallest unit of matter that still has the identity and properties of that particular element. In other words, if you have an atom of carbon, you have a tiny, very, very tiny piece of carbon, has all the properties of carbon, it looks like carbon, it acts like carbon. Anything smaller than that would be subatomic particles, and those do not have the properties of anything. But an atom of carbon is the smallest piece of carbon you can have. All matter, without exception, is made of atoms. They may be single atoms if it's an element, and they may be multiple atoms in, say, a compound. So water, H2O, is hydrogen and oxygen, 3 atoms total of 2 different elements. That's a compound. Hydrogen and oxygen are elements. They can't be made simpler, and they are all made up of atoms. Atoms are unbelievably small. It's almost impossible to really comprehend just how small atoms really are. If one were to look at an atom, if one could see them, they would look something like a fuzzy ball of cotton. That fuzz is the electron cloud. And in the center of the atom is the nucleus. The nucleus is very small compared to the total size of the atom, and yet the nucleus has most of the mass of the atom in it. So even though it's small, it's dense. It's made up of 2 subatomic particles, protons and neutrons. And again, when we're measuring the mass of an atom, the only thing we really need to measure is the nucleus, because the rest of it, the electron cloud, has very little mass, so it doesn't contribute much to the total mass. The nucleus, I should say, is positively charged, and that's because it's only made up of the protons, which are positive, and the neutrons, which being neutral, have no effect on the charge. So the total charge of the nucleus is positive. The electron cloud, on the other hand, is negative. When you add them together, they cancel out. So most atoms are neutral. So we begin with the 3 subatomic particles, protons, neutrons, electrons. And we'll start with the proton, because the proton is the one that tells you what the element is. These are small, positively charged particles. They are in the nucleus. And if you know the number of protons, you know what the element is. Because, again, using carbon as an example, carbon atoms all have 6 protons, no exception. If it has more or less than 6, it would no longer be carbon. 6 protons is the number that makes an atom a carbon atom and not nitrogen or gold or anything else. So if you know the number of protons, what we call the atomic number, that will give you the identity of the element. And that's pretty much what protons do. They give an element its identity. Neutrons are also in the nucleus. They are about the same size, a little bit larger than a proton, but we count them as more or less the same size. And the big difference between a proton and neutron is that neutrons have no charge. They do not have a positive charge. So they don't contribute to the charge of the atom, and they also don't change the identity. And this is interesting in that you can have 2 atoms of the same element, but they may not have the same number of neutrons. It turns out that atoms of one element are not identical necessarily the way we thought they were. But changing the number of neutrons doesn't change what an element is. The only thing it would change would be the mass of the atom, because you have more or less mass depending on whether you have more or less neutrons. And the third and the most important subatomic particle in terms of what it is that an element does is the electron. Electrons are small particles that, instead of being in the nucleus, are kind of buzzing around the nucleus in these orbitals. But if you were to see them, you don't actually see them. They're moving very fast, almost at the speed of light. So they just appear to be a blur. And that's what makes the electron cloud cloudy. It's this electrons jumping around, buzzing about. They tend to stay in some areas more than others, but it's hard to predict exactly where an electron is. The number of electrons is what will make an atom very reactive, like sodium, or very unreactive, like helium. It turns out that there are certain numbers of electrons that are stable and make an atom stable. And a stable atom doesn't really want to do very much. But only a few atoms have that stability. The others don't. They try to get that way by either taking in more electrons or throwing them away to try to get to a stable number. Now, of course, if you throw away something that's negative, what's left behind is more positive than it was before the electrons left. So now we have a positive atom. And if another atom takes those electrons, they become negative. See, now we've changed everything. We've gone from atoms that were positive to atoms that were neutral to atoms that were positive and negative, and opposites attract. So I've mentioned already the electron cloud. The electron cloud is an area around the nucleus where you will find the electrons. Now, this is a much larger area than the nucleus itself. When they draw atoms, they usually make them a little deceptive. They make them bigger than they really should be because we want to be able to see them. But in reality, if you were to see an electron cloud, what you would see is just a very large fuzzy area that takes up most of the space in the atom. So the electron cloud has almost all the volume of the atom, but the atom's nucleus is where most of the mass is. I think it's been described that if an atom were the size of a beach ball, it would only be a tiny little grain of sand in the center that would really be the nucleus. And yet that's, again, where the mass is. The model of the atom that you're all used to seeing is this one, what we call the Bohr model. The Bohr model is kind of like the nucleus is the sun in the center, and the electrons are zipping around it in very defined pathways, kind of like the orbit of planets around the sun. And while this is a great model, and it shows us, nucleus is in the center, positive nucleus in the center, the negative electrons are going around it, it's not really accurate. This is not what atoms look like. So just keep in mind, the Bohr model, although it's a nice model, is not really accurate. One of the most important concepts, the one thing I would really want you to remember, is the idea of valence electrons. So here we see an atom, and I see 2, 10, 1, 2, 3, 4, 5, 6, 7, 8. This looks like it has 18 electrons total. But all that's really important is the very last layer of electrons, that outer shell where I count 1, 2, 3, 4, 5, 6, 7, 8. This, I believe, is an atom of argon. Argon is a gas element that does nothing. It will not react with anything. And why? Because it's got 8 valence electrons, and 8 is like a magic number. 8 valence electrons is an atom that is very, very happy, very satisfied, does not have any need to gain or lose electrons, and therefore will not be positive or negative. Knowing that this has 8 valence electrons, even if I didn't know anything about argon, I could say this is an atom that is going to do almost nothing. It's not going to react with much of anything. So you can see the power of understanding valence electrons. If you know how many valence electrons there are, you can say this is a metal, it's going to give up electrons. This is a non-metal, it's going to gain electrons. It's got 7, it wants 8. This is going to be a very reactive element. It's got 1, also a reactive element. The number of valence electrons is really the key to understanding what an element will do. So we're going to spend quite a bit of time talking about that. So just remember, none of the other electrons really matter. It's only that last outer layer of valence electrons that will determine what an element does. They're so important that we came up with a real easy way of showing them. And that's Lewis dot diagrams, sometimes called electron dot diagrams or Lewis structures. And this is a nice, easy shorthand for showing just the important electrons, the valence electrons. You put the symbol of the element, the 1 or 2 letters that we use to symbolize the element, Li for lithium, O for oxygen, N for nitrogen, and so on. And you put a dot for every valence electron there is. The maximum number you can have is 8. There has to be at least one valence electron, and there can be a maximum of 8. So looking at this, I can see lithium, beryllium, boron. These have 1, 2, and 3 valence electrons. These are metals. Now, I said they want to get to 8. 1, 2, and 3 is pretty far away from 8. What would be much easier, instead of trying to steal 7, 6, or 5 electrons, would be to just throw those electrons away. Just toss them away, and that whole layer disappears. And the layer that's underneath that layer is full, which is what they really want. They want a full layer of valence electrons. 8's usually the number that gets you there. In the case of nitrogen, it's got 5. Throwing away 5 is not easy, but gaining 3 is easier. Oxygen only has to gain 2. Chlorine only has to gain 1. Now you can see why chlorine is so dangerous. It's so close to having what it needs, which is just 1 more electron in its valence shell. So you put your hand into chlorine gas and it starts stealing those electrons from your hand, causing your hand to begin to disintegrate. Argon, on the other hand, look at it, it's got 8 valence electrons, 8 dots. Well, I can look at this, so that if I didn't know anything about argon, I can look at it and say, nothing's going to happen here. This is not an atom that's going to throw away or gain. It's perfectly happy. So the electron dot diagram, just by looking at it, you should instantly be able to figure out what it is that this element is going to do. Throw away electrons if it's got 3 or less, gain electrons if it's got 5 or more. And if it's got 8, do nothing. The atomic number is the number of protons. They are one and the same. If they give you one, if they say this has an atomic number of 8, it's as if they just said it's got 8 protons. And if they tell you I have an element with 8 protons, it's got an atomic number of 8. That's just what they are. It's usually at the top of the little box they have for the periodic table. But if you're ever confused, and different periodic tables have these in different ways, there's always 2 numbers. There's the atomic number and there's the atomic mass. The atomic mass is the protons and the neutrons, and the atomic number is just the protons. So obviously, the atomic number will be the smaller of the 2 numbers because the atomic mass includes the atomic number in it, plus other things. We arrange the periodic table in terms of atomic numbers. So hydrogen with 1 atomic number is 1, helium is 2, and so on. And this was one of the great discoveries of humankind, to figure out how to arrange the periodic table and discover the 92 elements that make up every single thing in the universe. Anything that is made of matter is made up of these elements. Mass number is we're going to measure the mass of an atom. Since the electrons are so small, we don't count them. So we simply take the number of protons, add the number of neutrons, and that's the mass number. Now, for one atom, that's going to be a whole number. I mean, one atom has, let's say, 7 protons and 5 neutrons for an atomic mass, a mass number of 12. But when you look at the symbol, the little box that they have everything in, a lot of times this mass number is not a whole number. It's like 11.3, and you might ask, how can it possibly be 0.3? I can't have 0.3 protons or 0.3 neutrons. Why is it not 11 or 12? And that's because of isotopes. Isotopes are when you have elements that have different, they're the same element, same kind of atom, but the atoms have different amounts of neutrons. And these are significant. Now they act the same. So here's 3 different kinds of hydrogen: hydrogen 1, hydrogen 2, and hydrogen 3. They all have 1 proton. They have to have 1 proton. If you don't have just 1 proton, you're not hydrogen anything. So the atomic number doesn't change. But hydrogen 1 is just a proton. There are no neutrons. Hydrogen 2 has a proton and a neutron. And hydrogen 3 has 1 proton, always, plus 2 neutrons. So they do have different atomic mass. And sometimes isotopes can be radioactive. but their chemical properties are going to be largely the same. To figure out the average atomic mass, we take the relative numbers of these different isotopes and come up with a number. We don't just add them all up and take and divide by whatever, take an average. We look at how often does hydrogen 2 show up? How often does hydrogen 3 show up? Because if we just took the average of 1, 2, and 3, the average would be 2. But the truth is, hydrogen 1 is like 99% of all the hydrogen you'll ever find. So when we do that weighted average, take a look here, the actual, it's 1.00794, which tells me that hydrogen 1 is by far the most common one, and 2 and 3 are very, very rare. So we weight the average to make sure that we get an accurate number and not just take all the different isotopes together and divide by the number and get something that's not going to be close to reality. So that is our vocabulary for beginning atomic structure. There's a lot of information. It can get a little confusing, but these are pretty simple concepts. So remember, protons positive in the nucleus, neutrons neutral in the nucleus, electrons negative in the clouds surrounding the nucleus. That tells you the charges and where you can find them. And then understand how it is that you're able to get each one. If they ask you for an atom, how many protons, how many neutrons, how many electrons, you'll be able to do that. And that will probably be the subject of our next video that we'll be doing on Wednesday. So you take care. I'll see you tomorrow. Bye now.